For more than a century, Tyrannosaurus rex has occupied a unique position in science and public imagination. It is often described as the ultimate predator, a massive carnivore with crushing jaws, powerful legs, and senses finely tuned for hunting. In the ecosystems of late Cretaceous North America, Tyrannosaurus rex stood at the very top of the food web. And yet, despite this apparent dominance, it disappeared entirely. Around 66 million years ago, Tyrannosaurus rex vanished from the fossil record, along with all other non-avian dinosaurs. No gradual decline unique to this species is evident. No competing predator replaced it. No evolutionary transition softened its disappearance. It was present, and then it was gone. This raises a question that is deceptively simple, but scientifically profound. If Tyrannosaurus rex was so successful, so specialized, and so dominant within its environment, why did it not survive? This question has often been framed incorrectly. Popular explanations tend to focus on singular causes, a catastrophic asteroid impact, volcanic eruptions, or sudden climate change. While these factors are undeniably important, they do not, on their own, explain why some organisms survived the same event, while Tyrannosaurus rex did not. To understand the extinction of T-Rex, we must go beyond asking what happened to the world. We must also ask what kind of organism Tyrannosaurus rex was and what kind of world it required to survive. Tyrannosaurus rex lived during the final stage of the Cretaceous period, between approximately 68 and 66 million years ago. Its known fossils are primarily found in western North America, within geological formations such as the Hell Creek Formation. This region was not a barren landscape. It was a complex environment composed of rivers, floodplains, forests, and coastal lowlands. Large herbivorous dinosaurs were abundant, including ceratopsians and hadrosaurs. These animals formed the energetic foundation of the ecosystem. Tyrannosaurus rex was adapted to exploit that foundation. Its anatomy reflects a predator specialized for overpowering and processing large prey. Its skull was massive and heavily reinforced. Its teeth were thick, robust, and capable of withstanding extreme forces. Evidence from bite marks on fossilized bones indicates that it could crush bone, allowing it to access nutrients unavailable to many other carnivores. These traits did not arise by chance. They reflect a long evolutionary history in which Tyrannosaurus rex and its close relatives became increasingly specialized as apex predators. By the late Cretaceous, this lineage had reached a peak in size and predatory capability. Importantly, there is no evidence that Tyrannosaurus rex was in decline prior to the end Cretaceous extinction. Fossil data suggest it was widespread and ecologically successful until the very end. This observation is critical. It means that Tyrannosaurus rex did not disappear because it was failing in its role as a predator. It disappeared because the conditions that supported that role ceased to exist. This distinction lies at the heart of modern scientific understanding of extinction. Extinction is rarely a judgment of strength or weakness. It is a consequence of mismatch. When environmental conditions change rapidly, organisms survive or perish not based on dominance, but on flexibility. The extinction of Tyrannosaurus rex must therefore be understood as the outcome of a collision between biological specialization and environmental catastrophe. In this documentary, we will examine that collision carefully. We will explore the biological characteristics that made Tyrannosaurus rex so successful, and the same characteristics that limited its ability to endure sudden global disruption. We will examine how large body size, high energy demands, and dependence on stable food webs shaped the fate of this animal. And we will place these biological realities within the broader context of the end Cretaceous extinction event. This approach requires caution. Science does not permit speculation beyond evidence. Where conclusions are drawn, they must rest on established principles of biology, ecology, and geology. Where uncertainty remains, it must be acknowledged openly. Tyrannosaurus rex has often been portrayed as a symbol of unstoppable power. But power, in evolutionary terms, is not measured by dominance alone. It is measured by persistence. The central question we will return to throughout this analysis is not whether Tyrannosaurus rex was strong enough to survive. It is whether the world that sustained Tyrannosaurus rex was capable of sustaining anything like it after the most dramatic mass extinction in Earth's history. By answering that question, we move beyond myth and toward understanding. In the sections that follow, we will begin by examining Tyrannosaurus rex as a biological organism, not as a monster or a legend, but as a real animal shaped by natural selection. Only then can we understand why even the most formidable predator could not outlast the collapse of the world it ruled. To understand why Tyrannosaurus rex could not survive the end Cretaceous catastrophe, we must first understand what kind of animal it truly was. Not a generic predator, not a flexible generalist, but a biological specialist, highly effective within a narrow ecological framework. Specialization is not a flaw in evolution. On the contrary, it is often the pathway to dominance. When environmental conditions are stable, organisms allowed to exploit resources with remarkable efficiency. Tyrannosaurus rex exemplified this principle. By the late Cretaceous, it represented the culmination of a lineage that had refined a very specific predatory strategy, the ability to subdue and process very large prey animals. This strategy is evident in its anatomy. Tyrannosaurus rex was among the largest terrestrial carnivores ever to exist, with adult individuals reaching lengths of over 12 meters and masses commonly estimated in the range of 8 to 9 metric tons. These estimates are derived from femoral circumference and other load-bearing skeletal elements, methods widely used in vertebrate paleontology. Large body size conferred several advantages. First, it allowed Tyrannosaurus rex to overpower prey animals that were themselves enormous. Late Cretaceous North America supported abundant populations of large herbivores, including hadrosaurs and ceratopsians. These animals provided vast quantities of energy, but accessing that energy required the ability to deliver decisive force. Second, large size reduced vulnerability to other predators. There is no evidence that adult Tyrannosaurus rex faced significant predation pressure from other carnivores. Its position at the top of the food web was secure. But size also imposed constraints. Large animals require large amounts of energy simply to maintain basic physiological processes. Metabolic demands scale with mass, and even conservative estimates indicate that Tyrannosaurus rex required substantial caloric intake on a regular basis. This dependence on abundant food tied its survival directly to the stability of the ecosystem beneath it. Its skull and jaws further reinforce this picture of specialization. Tyrannosaurus rex possessed one of the most robust skulls known among theropod dinosaurs. The bones of the skull were thick, heavily fused, and capable of withstanding extreme forces. Its teeth were not thin blades designed for slicing, but thick conical structures adapted to resist fracture.
Bite force estimates, derived from biomechanical modeling, suggest that Tyrannosaurus rex could generate forces sufficient to crush bone. This capability is supported by direct fossil evidence, bite marks and crushed bones found on the remains of large herbivores, some showing signs of healing, indicating interaction with living prey. Bone crushing is an energetically efficient feeding strategy. By consuming bones in addition to soft tissue, Tyrannosaurus rex could extract nutrients unavailable to predators that relied solely on flesh. This reduced competition and maximized energy return per kill. However, this strategy depended on one crucial condition: the continued presence of large-bodied prey animals. Tyrannosaurus rex was not adapted for a diet of small, rapidly reproducing animals. Its body size, jaw mechanics, and hunting style were all optimized for infrequent but high-yield feeding events. This contrasts sharply with generalist predators, which can shift between prey types as availability changes. Sensory adaptations also reflect specialization. Studies of the brain case and cranial nerves indicate that Tyrannosaurus rex possessed a highly developed sense of smell. This would have been advantageous for locating carcasses over long distances and tracking prey in complex environments. Its visual system, inferred from orbital structure and brain morphology, suggests forward-facing eyes and good depth perception, traits consistent with an ambush-capable predator. These sensory strengths improved hunting efficiency, but they did not increase dietary flexibility. They enhanced Tyrannosaurus rex's performance within its existing niche rather than enabling it to exploit new ones. Reproductive biology further constrained adaptability. While direct evidence of Tyrannosaurus rex reproduction is limited, comparisons with living reptiles and birds, as well as growth ring analysis in bones, suggest relatively slow maturation compared to small animals. Large body size generally correlates with longer growth periods and lower reproductive output. In stable environments, this is not a disadvantage. Populations remain steady, and offspring survival rates can be high. In rapidly changing or catastrophic conditions, however, slow reproduction becomes a liability. Species that reproduce quickly can rebound from population losses. Species that do not, cannot. Another critical aspect of specialization lies in thermoregulation and physiology. Although the exact metabolic strategy of Tyrannosaurus rex remains debated, there is broad agreement that it did not function like modern cold-blooded reptiles. Bone histology and growth rates suggest a more active physiology, likely intermediate between traditional reptilian ectothermy and modern avian endothermy. Such a physiology would support active hunting, but it would also increase baseline energy requirements. In other words, Tyrannosaurus rex was built for performance, not endurance under scarcity. This distinction is essential. Evolution does not select organisms to survive every conceivable future scenario. It selects organisms that succeed under prevailing conditions. For millions of years, the late Cretaceous environment provided exactly the conditions Tyrannosaurus rex required: abundant large prey, relatively warm global climates, and stable, productive ecosystems. Within that context, its specialization was not a weakness, it was a triumph. But specialization narrows the range of viable environments. As long as the ecological foundation remained intact, Tyrannosaurus rex thrived. When that foundation began to fracture, its options were limited. This sets the stage for understanding extinction not as a sudden failure of an organism, but as the loss of compatibility between biology and environment. In the next section, we will examine how the world of the late Cretaceous began to change even before the final catastrophe, and how these changes placed increasing stress on organisms that depended on stability.
The biological success of Tyrannosaurus rex was not accidental. It emerged from a precise alignment between anatomy, physiology, and environment. Yet that same precision imposed limits. Adaptation is never absolute. It is always conditional. To understand why Tyrannosaurus rex could not persist through the end Cretaceous crisis, we must examine how its greatest strengths were inseparable from constraints that reduced its ability to respond to rapid change. The first of these constraints is scale. Large body size offers clear advantages in predation, greater force generation, dominance over prey, and reduced vulnerability to other predators. But size also dictates energy economics. All large animals face a fundamental biological reality. Their daily survival depends on the continuous availability of substantial energy inputs. Even if Tyrannosaurus rex did not hunt daily, it required ecosystems capable of sustaining large herbivore populations over long periods. Its existence was therefore indirectly dependent on primary productivity, the ability of plants to convert sunlight into biomass. This dependency placed Tyrannosaurus rex several steps removed from the base of the food web. Such distance amplifies risk. When energy flow through an ecosystem is disrupted, the effects are magnified at higher trophic levels. A decline in plant productivity first impacts herbivores. Only later do apex predators experience the full consequences. This delay can create the illusion of resilience, but it also limits response time. Another critical adaptive strength was mechanical specialization. The skeletal architecture of Tyrannosaurus rex revealed a body optimized for delivering and absorbing high forces. Robust limb bones supported sudden acceleration and deceleration. Reinforced joints minimized failure under stress. The skull, with its thickened bones and tightly interlocking elements, was capable of withstanding repeated high-load biting. This allowed Tyrannosaurus rex to employ a feeding strategy that combined active predation with opportunistic scavenging.
Such versatility improved efficiency within its niche. However, mechanical specialization narrows functional breadth. A skull built for bone crushing is not optimized for delicate feeding. A body designed to overpower large prey is not well suited to exploiting small, elusive animals. These trade-offs are universal in biology. Adaptations enhance performance in one context at the expense of others. Physiological constraints further limited flexibility. Evidence from bone microstructure suggests that Tyrannosaurus rex grew rapidly during juvenile stages, reaching large adult sizes in a relatively short geological time. Rapid growth requires high nutrient intake and stable conditions. Once adulthood was reached, growth slowed, but maintenance costs remained high. Large muscle mass, dense bone, and active tissues require constant metabolic support. Such versatility improved efficiency within its niche. However, mechanical specialization narrows functional breadth. A skull built for bone crushing is not optimized for delicate feeding. A body designed to overpower large prey is not well suited to exploiting small, elusive animals. These trade-offs are universal in biology. Adaptations enhance performance in one context at the expense of others. Physiological constraints further limited flexibility. Evidence from bone microstructure suggests that Tyrannosaurus rex grew rapidly during juvenile stages, reaching large adult sizes in a relatively short geological time. Rapid growth requires high nutrient intake and stable conditions. Once adulthood was reached, growth slowed, but maintenance costs remained high. Large muscle mass, dense bone, and active tissues require constant metabolic support. Periods of prolonged scarcity would place immediate stress on such systems. Unlike smaller animals, Tyrannosaurus rex could not significantly reduce its energy requirements through behavioral strategies such as hibernation, burrowing, or long-term torpor. Its physiology was tuned for activity, not dormancy. Thermoregulation presents another dimension of constraint. While the exact metabolic classification of Tyrannosaurus rex remains debated, there is broad agreement that it occupied an intermediate physiological state, more active than modern reptiles, but not fully endothermic like birds or mammals. This condition would have allowed effective hunting while limiting some metabolic costs. Yet even intermediate metabolic strategies require environmental stability. Abrupt temperature changes, whether cooling or heating, impose physiological stress. Large-bodied animals dissipate heat slowly and respond sluggishly to rapid thermal shifts. As climate variability increases, thermal inertia becomes a liability rather than an asset. Behavioral flexibility is often cited as a potential buffer against environmental change. However, there is no evidence that Tyrannosaurus rex possessed the behavioral repertoire necessary to radically alter its lifestyle. There is no indication of seasonal migration across vast distances, no evidence of shelter building, no evidence of dietary generalism comparable to omnivorous species. These absences do not indicate inferiority, they reflect evolutionary priorities. Tyrannosaurus rex did not need such strategies in a world where large prey was abundant and climatic conditions were relatively stable. Reproductive strategy further constrained adaptability. Large vertebrates typically exhibit lower reproductive rates than small animals. They invest heavily in individual offspring, requiring longer periods to reach maturity. In stable environments, this strategy supports population stability. In disturbed environments, it slows recovery. When population numbers decline sharply, species with rapid reproduction can rebound within a few generations. Such versatility improved efficiency within its niche. However, mechanical specialization narrows functional breadth. A skull built for bone crushing is not optimized for delicate feeding. A body designed to overpower large prey is not well suited to exploiting small, elusive animals. These trade-offs are universal in biology. Adaptations enhance performance in one context at the expense of others. Physiological constraints further limited flexibility.
Evidence from bone microstructure suggests that Tyrannosaurus rex grew rapidly during juvenile stages, reaching large adult sizes in a relatively short geological time. Rapid growth requires high nutrient intake and stable conditions. Once adulthood was reached, growth slowed, but maintenance costs remained high. Large muscle mass, dense bone, and active tissues require constant metabolic support. Such versatility improved efficiency within its niche. However, mechanical specialization narrows functional breadth. A skull built for bone crushing is not optimized for delicate feeding. A body designed to overpower large prey is not well suited to exploiting small, elusive animals. These trade-offs are universal in biology. Adaptations enhance performance in one context at the expense of others. Physiological constraints further limited flexibility. Evidence from bone microstructure suggests that Tyrannosaurus rex grew rapidly during juvenile stages, reaching large adult sizes in a relatively short geological time. Rapid growth requires high nutrient intake and stable conditions. Once adulthood was reached, growth slowed, but maintenance costs remained high. Large muscle mass, dense bone, and active tissues require constant metabolic support. Periods of prolonged scarcity would place immediate stress on such systems. Unlike smaller animals, Tyrannosaurus rex could not significantly reduce its energy requirements through behavioral strategies such as hibernation, burrowing, or long-term torpor. Its physiology was tuned for activity, not dormancy. Thermoregulation presents another dimension of constraint. While the exact metabolic classification of Tyrannosaurus rex remains debated, there is broad agreement that it occupied an intermediate physiological state, more active than modern reptiles, but not fully endothermic like birds or mammals. This condition would have allowed effective hunting while limiting some metabolic costs. Yet even intermediate metabolic strategies require environmental stability. Abrupt temperature changes, whether cooling or heating, impose physiological stress. Large-bodied animals dissipate heat slowly and respond sluggishly to rapid thermal shifts. As climate variability increases, thermal inertia becomes a liability rather than an asset. Behavioral flexibility is often cited as a potential buffer against environmental change. However, there is no evidence that Tyrannosaurus rex possessed the behavioral repertoire necessary to radically alter its lifestyle. There is no indication of seasonal migration across vast distances, no evidence of shelter building, no evidence of dietary generalism comparable to omnivorous species. These absences do not indicate inferiority, they reflect evolutionary priorities. Tyrannosaurus rex did not need such strategies in a world where large prey was abundant and climatic conditions were relatively stable. Reproductive strategy further constrained adaptability. Large vertebrates typically exhibit lower reproductive rates than small animals. They invest heavily in individual offspring, requiring longer periods to reach maturity. In stable environments, this strategy supports population stability. In disturbed environments, it slows recovery. When population numbers decline sharply, species with rapid reproduction can rebound within a few generations.
Species with slow life histories cannot. This difference becomes decisive during mass extinction events. Another subtle but important limitation arises from ecological role. As an apex predator, Tyrannosaurus rex did not simply consume energy, it regulated the structure of the ecosystem beneath it. Such regulation depends on equilibrium. When equilibrium collapses, apex predators have no higher-level refuge. They cannot shift upward in the food web. They can only follow the system downward. In contrast, organisms occupying lower trophic levels often have more options. They may switch food sources, alter behavior, or exploit microhabitats. The apex position that once conferred dominance becomes a position of exposure. It is crucial to emphasize that none of these limitations imply inadequacy. Tyrannosaurus rex was not poorly adapted. It was precisely adapted, perhaps too precisely, to a particular ecological configuration. This distinction is essential. Adaptation optimizes organisms for present conditions, not future catastrophes. The fossil record does not show Tyrannosaurus rex failing prior to the extinction event. On the contrary, it suggests continued ecological success until the final boundary. This indicates that the limits we identify were not apparent until environmental change exceeded the range within which adaptation could function. At this point, a critical insight emerges. The extinction of Tyrannosaurus rex cannot be explained solely by the magnitude of the catastrophe that followed. It must also be understood through the lens of biological constraints that limited the species' capacity to absorb shock. The question is no longer whether Tyrannosaurus rex was strong enough to survive. The question becomes whether any organism with its biological profile could have survived under those conditions. This reframing prepares us for the central transition of the documentary. In the next section, we will shift our attention from the organism to the world itself, examining the environmental stresses that were already shaping the late Cretaceous before the final catastrophic event occurred. It is at that intersection between biological limits and environmental instability that extinction becomes inevitable. Long before the asteroid impact that marks the end of the Cretaceous period, the world inhabited by Tyrannosaurus rex was already undergoing significant environmental stress. This point is essential. The end Cretaceous extinction did not strike a perfectly stable world. It struck an ecosystem that, while still functioning, was increasingly strained. Understanding this context helps explain why even a highly successful apex predator could not endure what followed. During the final few million years of the Cretaceous period, Earth experienced notable climatic and environmental variability. Geological evidence indicates fluctuations in temperature, changes in sea level, and disruptions to atmospheric chemistry. Sea levels, which had been relatively high for much of the Cretaceous, began to regress in several regions. As shallow inland seas retreated, coastlines shifted, altering habitats and nutrient cycles. In western North America, where Tyrannosaurus rex lived, these changes reshaped floodplains, river systems, and vegetation patterns. Such environments are productive but sensitive. Small changes in precipitation or temperature can have cascading effects on plant communities. Because primary productivity underpins the entire food web, even modest disruptions at this level can propagate upward. At the same time, one of the most extensive volcanic events in Earth's history was unfolding on the opposite side of the planet.
The Deccan Traps of present-day India represent a series of massive volcanic eruptions that occurred over hundreds of thousands of years near the end of the Cretaceous. These eruptions released enormous quantities of gases, including carbon dioxide and sulfur dioxide, into the atmosphere. The climatic effects of such emissions are complex. Carbon dioxide contributes to long-term warming, while sulfur aerosols can cause short-term cooling by reflecting sunlight. The interaction of these opposing forces likely produced periods of climatic instability rather than a single uniform trend. Importantly, these effects were global. Atmospheric circulation distributes volcanic emissions across continents. Even ecosystems far from the eruption site would have experienced altered temperature regimes, changes in rainfall patterns, and episodes of acid deposition. For large terrestrial ecosystems, this meant increased unpredictability. Plants adapted to stable conditions can tolerate gradual change, but repeated or rapid fluctuations challenge their capacity to recover. As plant communities shift, herbivore populations respond, sometimes declining, sometimes migrating, sometimes reorganizing their feeding strategies. For a predator such as Tyrannosaurus rex, these changes were indirect but consequential.
Apex predators are insulated by minor environmental fluctuations by the buffering capacity of lower trophic levels. They do not immediately experience the effects of droughts or temperature shifts. However, this insulation comes with a cost. It delays feedback. When prey populations decline, the effect on predators is not immediate, but when it arrives abruptly. Fossil evidence from late Maastrichtian formations does not suggest that Tyrannosaurus rex populations were collapsing prior to the extinction boundary. Large herbivores were still present, and the ecosystem remained broadly functional. Yet there are indications that ecological margins were narrowing. Some studies suggest changes in herbivore diversity and abundance toward the end of the Cretaceous. Others point to increased ecological stress inferred from plant fossil assemblages and geochemical proxies. These signals are subtle. They do not indicate imminent collapse, but they suggest a system operating with reduced resilience. Resilience, in ecological terms, refers to the ability of a system to absorb disturbance without shifting into a fundamentally different state. Highly productive ecosystems can absorb small shocks repeatedly, but as stress accumulates, the threshold for collapse lowers. For large-bodied specialists like Tyrannosaurus rex, reduced resilience elsewhere in the system poses a particular risk. Because Tyrannosaurus rex depended on large prey populations, it required not only the presence of those animals, but the stability of the processes that sustained them. Herbivores require consistent access to vegetation. Vegetation requires predictable sunlight, temperature, and water availability. Disrupt any one of these for long enough, and the system begins to falter. Another factor to consider is geographic constraint. Tyrannosaurus rex is currently known only in North America. Unlike some organisms with broad global distributions, it did not occupy multiple continents with potentially different environmental conditions. This limited geographic range reduced the species' options. If conditions deteriorated across its entire habitat, there was no distant refuge to which populations could retreat. Geographic restriction amplifies vulnerability during global or continental scale disruptions.
At the same time, biological specialization compounded this risk.
As discussed in earlier sections, Tyrannosaurus rex was optimized for a specific ecological role. It was not adapted for long-distance migration across drastically different environments. Its size and physiology favored efficiency within known landscapes rather than exploratory flexibility. Taken together, these factors created a situation in which Tyrannosaurus rex was surviving successfully, but with little margin for error. This is a critical distinction. Extinction is often imagined as the result of prolonged decline. In many cases, however, extinction results from sudden, boundary-crossing events that overwhelm systems already operating near their limits. By the late Maastrichtian, the world was not collapsing, but it was less forgiving. Environmental stress did not eliminate Tyrannosaurus rex on its own. There is no evidence for a gradual replacement or competitive exclusion. Instead, these stresses acted as background conditions that reduced the capacity of the ecosystem to absorb additional shocks. This sets the stage for the central turning point of the documentary. The asteroid impact at the end of the Cretaceous did not occur in isolation. It struck a world that had already been shaped by volcanic activity, climatic variability, and ecological tension. When that impact occurred, the system did not have the resilience it might once have possessed. For organisms with broad diets, rapid reproduction, or flexible behaviors, this loss of resilience could be survivable. For a large, specialized apex predator, it was catastrophic. This brings us to a crucial reframing of the extinction narrative. The question is not simply what caused the extinction event. The question is why the event proved fatal to some organisms and not others. To answer that, we must now shift our focus to the moment of maximum disruption and the assumptions we make about what actually ended the age of dinosaurs. In the next section, we will pause and reconsider the way this story is usually told. Because the most common question, what killed Tyrannosaurus rex, may not be the most informative one. At this point in the story, it is tempting to ask a familiar question. What killed Tyrannosaurus rex? The question is intuitive. It implies a single cause, a decisive blow, a moment of defeat. But science rarely works that way. When we examine mass extinctions through the lens of ecology and biology, the most revealing answers often emerge from a different question entirely. Not what killed Tyrannosaurus rex, but what kind of world could no longer support it. This distinction matters, because extinction is not an act of violence against a species. It is a breakdown of compatibility between organisms and their environment. Tyrannosaurus rex did not disappear because it was suddenly overpowered. It disappeared because the conditions that sustained its existence were removed. Reframing the problem in this way shifts our attention from dramatic events to biological realities. It forces us to examine extinction not as an isolated incident, but as a process governed by thresholds. In stable ecosystems, organisms exist within a range of tolerable conditions. Temperature, food availability, habitat structure, and ecological interactions fluctuate within limits. As long as these fluctuations remain within a species' tolerance range, populations persist. When those limits are exceeded, especially rapidly, extinction becomes possible. For a large, specialized apex predator, those tolerance ranges are narrow.
This is not a criticism, it is a consequence of evolutionary optimization. Tyrannosaurus rex was highly effective within a specific ecological... At this point in the story, it is tempting to ask a familiar question. What killed Tyrannosaurus rex? The question is intuitive. It implies a single cause, a decisive blow, a moment of defeat. But science rarely works that way. When we examine mass extinctions through the lens of ecology and biology, the most revealing answers often emerge from a different question entirely. Not what killed Tyrannosaurus rex, but what kind of world could no longer support it. This distinction matters, because extinction is not an act of violence against a species. It is a breakdown of compatibility between organisms and their environment. Tyrannosaurus rex did not disappear because it was suddenly overpowered. It disappeared because the conditions that sustained its existence were removed. Reframing the problem in this way shifts our attention from dramatic events to biological realities. It forces us to examine extinction not as an isolated incident, but as a process governed by thresholds. In stable ecosystems, organisms exist within a range of tolerable conditions. Temperature, food availability, habitat structure, and ecological interactions fluctuate within limits. As long as these fluctuations remain within a species' tolerance range, populations persist. When those limits are exceeded, especially rapidly, extinction becomes possible. For a large, specialized apex predator, those tolerance ranges are narrow. This is not a criticism, it is a consequence of evolutionary optimization. Tyrannosaurus rex was highly effective within a specific ecological configuration: warm climates, high primary productivity, and abundant large-bodied herbivores. Within that configuration, it flourished. Outside it, survival options diminished quickly. This brings us to a critical insight. Mass extinctions do not select organisms based on how powerful they are. They select based on how flexible they are. This principle is supported repeatedly in the fossil record. Across the end Cretaceous boundary, many groups with long evolutionary histories vanished. Others, often smaller, more generalized, or behaviorally flexible, survived. This pattern suggests that survival during global crises depends less on dominance and more on adaptability. Understanding this helps resolve a common misconception. The asteroid impact at the end of the Cretaceous did not target Tyrannosaurus rex. It did not discriminate. Its effects propagated through physical systems, atmosphere, oceans, and land, altering the flow of energy that sustained life. The consequences were ecological, not selective. Photosynthesis was disrupted. Plant growth declined. Food webs destabilized. These changes did not need to persist for millions of years to be lethal. They only needed to last long enough to exceed biological limits. For small animals with low energy demands, this window could be survivable. For large animals dependent on continuous energy flow, it could not. This is where asking the wrong question leads to misunderstanding. If we ask what killed Tyrannosaurus rex, we focus on the moment of impact. If we ask what kind of world Tyrannosaurus rex required, we focus on duration, dependency, and resilience. From this perspective, extinction becomes a matter of timing. How long did primary productivity decline? How quickly did herbivore populations collapse? How long could apex predators endure without adequate food? These questions are far more relevant to survival than the magnitude of the initial disturbance alone. They also explain why extinction unfolded unevenly. Some organisms survived the immediate aftermath only to disappear later. Others endured through the crisis and diversified afterward. Tyrannosaurus rex appears to have fallen into the category of organisms that could not bridge the gap between a functioning ecosystem and a fundamentally altered one. This does not require assuming immediate death. In fact, current scientific understanding suggests that extinction likely occurred over a relatively short geological interval, thousands, not millions of years, but not instantaneously. This timescale is crucial. It implies that Tyrannosaurus rex may have persisted briefly after the initial catastrophe, struggling within an environment that could no longer sustain large predators. As prey populations dwindled, competition among carnivores would have intensified. Energy deficits would have accumulated. Reproduction would have slowed or ceased. Eventually, populations would have fallen below viable levels. This process is consistent with ecological models and with patterns observed in other mass extinctions. It also underscores a central lesson. Extinction is not always the result of direct mortality. It is often the result of prolonged inability to meet basic biological requirements. Seen in this light, the extinction of Tyrannosaurus rex becomes less mysterious and more instructive. It illustrates the limits of specialization. It demonstrates the vulnerability of apex predators to systemic collapse. And it reminds us that evolutionary success is always contingent. The most important consequence of this reframing is that it prepares us to examine the next phase of the story with greater clarity. When we turn to the Chicxulub impact itself, we will do so not as an isolated cause, but as a trigger that pushed an already stressed system beyond recovery. We will examine what happened physically at the end of the Cretaceous, but we will interpret those events through the lens of biological tolerance and ecological dependency. Only then can we understand why the end of the dinosaurs was not simply a story of destruction, but a story of limits. In the next section, we will focus on the Chicxulub impact and its immediate global consequences, not to dramatize the event, but to evaluate its capacity to alter the basic conditions of life on Earth. Because it is only by understanding those conditions that we can fully answer the question we have reframed. Not what killed Tyrannosaurus rex, but why the world that sustained it could no longer exist.
66 million years ago, Earth experienced one of the most consequential geological events in its history. A large asteroid, estimated to be roughly 10 to 15 kilometers in diameter, struck the planet near what is now the Yucatan Peninsula in present-day Mexico. This impact created the Chicxulub crater, a structure more than 180 kilometers wide, now buried beneath younger sediments. The existence of this crater is not speculative. It is supported by geophysical surveys, drilling cores, and multiple independent lines of geological evidence. The timing of the impact coincides precisely with the boundary between the Cretaceous and Paleogene periods, the moment at which Tyrannosaurus rex and all other non-avian dinosaurs disappear from the fossil record. This temporal alignment is one of the strongest pieces of evidence linking the impact to the mass extinction. The immediate physical effects of the impact were extreme. Upon collision, an enormous amount of energy was released, far exceeding that of any volcanic eruption or nuclear detonation known in human history.
The asteroid vaporized instantly, along with a significant volume of the Earth's crust at the impact site. Shock waves radiated outward, triggering earthquakes on a global scale. Near the impact zone, temperatures rose dramatically within seconds. Materials were ejected high into the atmosphere and beyond. These effects alone were catastrophic locally, but local destruction does not explain global extinction. To understand why the Chicxulub impact mattered biologically, we must follow the energy beyond the crater. One of the most important consequences was the injection of vast quantities of dust, soot, and sulfate aerosols into the upper atmosphere. The asteroid struck carbonate and sulfate-rich rocks. This composition is critical. When vaporized, these rocks produced fine particles capable of remaining suspended in the atmosphere for extended periods. Additionally, global wildfires, ignited by thermal radiation from re-entering ejecta, likely contributed large amounts of soot. Together, these materials altered the transparency of the atmosphere. Sunlight reaching the Earth's surface was dramatically reduced. This reduction did not need to be total or permanent to have devastating consequences. Photosynthesis depends on light availability within relatively narrow thresholds. Even a sustained partial reduction in sunlight can disrupt plant growth across large regions. Geochemical evidence supports this scenario. At the Cretaceous-Paleogene boundary, a thin global layer enriched in iridium, a metal rare in Earth's crust but common in asteroids, is found in sedimentary rocks worldwide. This layer marks the fallout of extraterrestrial material following the impact. Associated with this layer are shocked quartz grains and microscopic spherules, further confirming the violent redistribution of material. The atmospheric effects translated quickly into ecological effects.
Plants form the base of terrestrial food webs. When photosynthesis declines, plant productivity drops. This does not immediately eliminate all vegetation, but it reduces growth rates, seed production, and recovery after damage. For herbivorous dinosaurs, this meant declining food availability. Large-bodied herbivores require vast quantities of plant material. They are sensitive to sustained reductions in productivity. As herbivore populations declined, the effects propagated upward. Apex predators, such as Tyrannosaurus rex, were not affected directly by reduced sunlight. They were affected by the disappearance of prey. This distinction is crucial. The impact did not kill Tyrannosaurus rex by physical force. It removed the energetic foundation upon which its survival depended. Climate disruption compounded these effects. In addition to reducing sunlight, atmospheric aerosols altered global temperature patterns. Models and proxy data suggest a period of rapid cooling following the impact, often referred to as an impact winter. Lower temperatures would have further stressed plant communities already struggling with reduced light. Cold snaps can damage plant tissues, shorten growing seasons, and disrupt reproductive cycles. For animals, temperature changes affect metabolism, behavior, and survival. Large-bodied animals like Tyrannosaurus rex possess significant thermal inertia. They do not adjust quickly to sudden temperature shifts. While this can buffer short-term fluctuations, it becomes a disadvantage when environmental change is prolonged. The duration of these post-impact conditions is a subject of ongoing research. However, most models indicate that significant disruption persisted for years, possibly decades.
From an ecological perspective, this timescale is critical. A few days or weeks of reduced productivity might be survivable for large animals. Years of disruption are not. Even if some prey animals survived the initial aftermath, their populations would have been fragmented and unstable. Reproductive rates would have declined. Mortality would have increased. For a predator dependent on consistent access to large prey, such instability is lethal. It is also important to emphasize what the impact did not do. There is no evidence that Tyrannosaurus rex populations were selectively targeted. There is no indication that large predators were uniquely vulnerable to the physical effects of the impact itself. The extinction pattern reflects ecological position, not direct exposure. Species lower in the food web, particularly those with flexible diets or dormant life stages, were more likely to survive. Species at the top, with high energy demands and narrow ecological roles, were not. This pattern is consistent across mass extinction events. The Chicxulub impact acted as a trigger, an event that rapidly altered global conditions beyond the tolerance limits of many organisms. But the impact alone does not explain why some lineages survived while others vanished. To understand that differential survival, we must examine how the collapse of food webs unfolded over time. The asteroid impact initiated the crisis. Ecological processes determined its outcome. In the next section, we will follow those processes in detail. We will examine how the breakdown of primary productivity cascaded through ecosystems, leading to the extinction of large terrestrial predators, and why recovery favored small, flexible organisms. Only by tracing this cascade can we fully understand why Tyrannosaurus rex could not endure the aftermath of the event that ended the age of dinosaurs.
When the immediate physical effects of the Chicxulub impact subsided, the most decisive phase of the extinction began. It was not marked by explosions or fire. It was marked by absence. The absence of light, the absence of growth, and ultimately the absence of energy moving through ecosystems. To understand why Tyrannosaurus rex could not survive this phase, we must examine how ecological systems respond when their foundational processes fail. At the base of terrestrial ecosystems lies primary productivity, the conversion of sunlight into chemical energy by plants. This process sustains herbivores, which in turn sustain carnivores. The Chicxulub impact disrupted this foundation. Atmospheric dust, soot, and aerosols reduced sunlight reaching the surface. Photosynthetic rates declined across large regions. Even modest reductions in light availability can have severe consequences when sustained over long periods. Plants may survive temporarily, but their ability to grow, reproduce, and recover from damage is compromised. Seed production declines, leaf growth slows, root systems weaken. For ecosystems dominated by large herbivores, this decline is particularly significant. Large herbivore dinosaurs required enormous quantities of vegetation. Their survival depended on the continuous regeneration of plant biomass. When plant productivity fell, herbivores faced nutritional stress. Body condition declined. Reproductive success decreased, juvenile mortality increased. These effects do not occur instantaneously, they accumulate over months and years. As herbivore populations declined,
the consequences for predators intensified. Apex predators do not experience food shortages gradually. They experience thresholds. As long as prey populations remain above a critical level, predators can persist. Below that level, survival becomes impossible. For Tyrannosaurus rex, this threshold was high. Its body size required large prey items to meet energy needs efficiently. Smaller prey could not compensate without increasing hunting frequency beyond sustainable limits. This creates a fundamental vulnerability. In a collapsing ecosystem, prey abundance does not decline evenly across size classes. Large-bodied herbivores are often among the first to disappear. They have higher energy requirements. They reproduce more slowly. They are less flexible in diet. As these animals declined, the prey base available to Tyrannosaurus rex contracted rapidly. Even if individual predators survived initial shortages, the population as a whole could not be maintained. Competition among carnivores would have intensified. As prey became scarce, scavenging opportunities increased briefly as carcasses accumulated. This may have provided short-term relief. But scavenging cannot sustain a large predator indefinitely. Once carcasses were consumed and herbivore populations continued to fall, food availability would have dropped precipitously. This transition from temporary abundance to prolonged scarcity is a well-documented pattern in ecological collapses.
Another important factor is spatial fragmentation. As ecosystems deteriorated, remaining resources became unevenly distributed. Vegetation persisted in some refuges, but disappeared in others. Herbivores would have concentrated in these refuges, increasing local competition and pressure on remaining plant resources. Predators dependent on wide-ranging movement faced additional challenges. Tyrannosaurus rex was not adapted for long-distance migration across drastically altered landscapes. Its large body size and energy requirements favored hunting within familiar, productive environments. As those environments fragmented, movement costs increased while rewards diminished. At the same time, ecological interactions became increasingly unstable. Predator-prey relationships depend on predictable dynamics. When prey availability fluctuates unpredictably, predators cannot optimize hunting strategies. Energy expenditure increases. Injury risk rises. Reproductive output declines. These stresses accumulate. Eventually, populations fall below viable levels. It is important to emphasize that this process did not require the immediate death of all individuals. Extinction often unfolds through population collapse rather than instantaneous mortality. A small number of Tyrannosaurus rex individuals may have survived for some time after the initial impact. However, without sufficient prey and declining reproductive success, these populations would have dwindled. Once population density falls below a critical threshold, extinction becomes inevitable. Random events, injury, disease, or failure to reproduce can eliminate the last remaining individuals. This dynamic helps explain why extinction boundaries appear sharp in the fossil record, even when the underlying process unfolds over years or decades. Lower trophic levels experienced different pressures. Small animals with flexible diets could exploit alternative food sources. Detritivores could feed on decaying organic matter. Omnivores could shift between plant and animal resources. Some organisms could enter dormant states or shelter underground, reducing energy needs. These strategies were not available to Tyrannosaurus rex.
Its biology did not permit long-term fasting without severe consequences. Its size precluded shelter-based survival strategies. Its specialized feeding apparatus was not suited to dietary generalism. This contrast underscores a central principle of ecological extinction dynamics. Survival during ecological collapse favors organisms with low energy demands, high reproductive rates, and flexible behaviors. Dominance under stable conditions offers no protection when those conditions vanish. Marine ecosystems experienced parallel processes. Plankton populations declined. Marine food webs collapsed from the bottom up. The similarity between terrestrial and marine extinction patterns strengthens the conclusion that energy disruption, not direct mortality, drove the mass extinction. Across environments, organisms dependent on continuous primary productivity suffered the greatest losses. Those capable of exploiting stored energy, dormant life stages, or alternative food sources fared better. Seen through this lens, the extinction of Tyrannosaurus rex becomes an expected outcome rather than a mystery. It was not singled out by catastrophe. It was outcompeted by circumstance. The ecological collapse following the Chicxulub impact removed the structural support required by large, specialized predators. Without sufficient energy flow, no amount of predatory efficiency could compensate. This brings us closer to the final phase of the analysis. We have examined the organism. We have examined the environment. We have traced the cascade from physical disruption to ecological collapse. What remains is to integrate these strands and explain why Tyrannosaurus rex, despite its evolutionary success, had no viable path through this crisis. In the next section, we will focus directly on that question. We will examine why Tyrannosaurus rex could not adapt quickly enough, and why adaptation itself has limits that even the most formidable species cannot overcome.
The end Cretaceous extinction compressed ecological change into an extremely short interval. Environmental conditions shifted faster than large vertebrate populations could respond evolutionarily. This mismatch between the pace of environmental change and the pace of biological adaptation is a defining feature of mass extinctions. It explains why even well-adapted species vanish. It also explains why survival is often concentrated among organisms with pre-existing traits that happen to confer resilience, not among those capable of evolving new ones in real time. In the case of Tyrannosaurus rex, there is no evidence that populations were already evolving towards smaller size, dietary flexibility, or faster reproduction prior to the extinction event. The fossil record shows continuity, not transition. This suggests that the environmental shift exceeded the adaptive capacity of the species before evolutionary responses could occur. It is important to clarify what adaptation did not fail. Tyrannosaurus rex did not fail to hunt effectively. It did not fail to compete within its niche. It did not fail due to disease or predation. It failed to persist because the niche itself disappeared. This distinction is critical for interpreting extinction scientifically. Adaptation does not guarantee survival under all conditions. It guarantees success only within the environmental envelope for which it evolved. When that envelope collapses, even the most specialized adaptations become irrelevant. This pattern is consistent across mass extinctions.
Large-bodied specialists are disproportionately affected. Small-bodied generalists are disproportionately represented among survivors. This outcome does not reflect superiority, it reflects compatibility. The inability of Tyrannosaurus rex to adapt in time therefore does not diminish its evolutionary success. On the contrary, it underscores how well adapted it was to a specific world. The tragedy, from a biological perspective, is that this world changed too quickly and too completely. As we approach the conclusion of this analysis, the focus shifts once more. We have examined the organism. We have examined the catastrophe. We have examined the collapse of ecosystems and the limits of adaptation. What remains is to place Tyrannosaurus rex within the broader pattern of survival and extinction at the end of the Cretaceous. In the next section, we will compare Tyrannosaurus rex with the organisms that did survive and identify the traits that allowed them to pass through one of Earth's greatest biological bottlenecks.
By the time the ecological consequences of the end Cretaceous crisis had fully unfolded, the world no longer resembled the one that Tyrannosaurus rex had dominated. Forests were sparse, primary productivity was diminished, food webs had been restructured from the bottom up. Yet life did not end. Some organisms endured, others disappeared entirely. Understanding this contrast is essential, not to diminish the significance of Tyrannosaurus rex, but to clarify the biological rules that govern survival during extreme change. One of the most striking patterns in the fossil record across the Cretaceous-Paleogene boundary is the survival of small-bodied organisms. Birds, which are the only living descendants of dinosaurs, persisted through the extinction event. So did many small mammals, reptiles, amphibians, and invertebrates. These survivors shared several key characteristics. First, they had lower absolute energy requirements. Small body size confers a fundamental advantage during resource scarcity. It reduces the minimum amount of energy needed to sustain vital functions. When food availability declines, smaller organisms can persist on limited resources that would be insufficient for large animals. Second, many survivors exhibited dietary flexibility. Early mammals were not specialized predators. They consumed a range of foods, including insects, seeds, carrion, and plant matter. This flexibility allowed them to exploit whatever resources remained available as ecosystems reorganized. Birds that survived the extinction appear to have been those capable of feeding on seeds or detritus, resources that could persist even when plant growth was suppressed. In contrast, organisms dependent on a narrow range of prey or food sources were disproportionately affected. Third, reproductive strategy played a critical role. Species with short generation times and high reproductive rates could recover from population declines more rapidly. They could also undergo evolutionary change more quickly, allowing selection to favor traits suited to the new environment. Large-bodied animals with slow reproduction lacked this capacity. Even if individual Tyrannosaurus rex survived the immediate aftermath, population recovery would have been extremely slow, assuming recovery was possible at all. Fourth, behavioral strategies favored survival. Many small animals could seek shelter underground, within burrows or crevices, reducing exposure to harsh surface conditions. Others could enter states of reduced metabolic activity, conserving energy during prolonged periods of scarcity.
There is no evidence that Tyrannosaurus rex possessed any comparable strategy. Its size and physiology precluded shelter-based survival. Its energy demands prevented extended metabolic suppression. This comparison reveals a central principle. Survival during mass extinction events favors organisms that can endure prolonged instability, not those optimized for peak performance under stable conditions. Dominance and endurance are not the same trait. Tyrannosaurus rex exemplified dominance.
It was supremely effective within its ecological context. Its anatomy, physiology, and behavior were finely tuned to a productive, stable environment. The organisms that survived exemplified endurance. They were not the most powerful. They were the most tolerant of deprivation, uncertainty, and change. This distinction helps resolve a common misunderstanding. Extinction is often imagined as a competition in which the strongest prevail. In reality, extinction is a filter that removes organisms whose requirements exceed what the environment can provide. During stable periods, that filter is permissive. During crises, it becomes ruthless. The end Cretaceous extinction was not a test of predatory ability. It was a test of ecological compatibility under extreme constraint. Viewed in this light, the disappearance of Tyrannosaurus rex is not paradoxical. It is predictable. A large apex predator occupies a position of maximum dependency. It depends on stable plant productivity, abundant herbivores, and predictable ecological interactions. Remove any one of these for long enough, and the system fails. The survivors of the extinction did not outcompete Tyrannosaurus rex. They outlasted the conditions that destroyed its world. This outcome carries a broader lesson for understanding evolution. Natural selection does not aim toward increasing complexity, size, or power. It favors traits that maximize reproductive success under prevailing conditions. When those conditions change abruptly, traits that once conferred advantage can become liabilities. This does not invalidate adaptation, it reveals its limits. Tyrannosaurus rex was not maladapted, it was exquisitely adapted to a world that vanished. This lesson extends beyond the end of the dinosaurs. Throughout Earth's history, mass extinctions have repeatedly reshaped life by eliminating dominant forms and opening ecological space for others. The survivors of these events are often unremarkable in isolation. Their significance lies in their capacity to persist through disruption. In the aftermath of the Cretaceous-Paleogene extinction, mammals diversified, birds radiated into new niches, ecosystems reassembled around different foundations. None of this required the defeat of Tyrannosaurus rex by a superior competitor. It required only the removal of the conditions that sustained it. As we approach the conclusion of this documentary, a final insight emerges. Extinction does not erase evolutionary success, it contextualizes it. Tyrannosaurus rex represents a peak, not of evolutionary progress, but of ecological specialization. Its extinction marks the end of a particular way of organizing life, not the failure of the organism itself. The story of its disappearance is therefore not a story of weakness, it is a story of limits. In the final section, we will draw these threads together. We will summarize what the extinction of Tyrannosaurus rex teaches us about adaptation, resilience, and the nature of survival on a changing planet. And we will reflect on why this lesson remains relevant, not as a warning about power, but as a reminder of how tightly life is bound to the conditions that sustain it. The extinction of Tyrannosaurus rex marks one of the most recognizable boundaries in the history of life on Earth. It represents not merely the disappearance of a single species, but the end of an entire ecological structure, a structure that had persisted for tens of millions of years. By tracing the fate of Tyrannosaurus rex through the lens of biology, ecology, and geology, a clear picture emerges. Its extinction was not sudden failure. It was not evolutionary inadequacy, and it was not defeat by a superior organism. It was the consequence of environmental change exceeding biological limits. Tyrannosaurus rex was a product of long-term evolutionary success. Its anatomy, physiology, and behavior reflect precise adaptation to a stable, productive late Cretaceous world. Large prey animals were abundant. Primary productivity was high. Food webs were robust and predictable. Within that framework, Tyrannosaurus rex occupied the apex. It was not merely dominant, it was integrated. Every aspect of its biology was aligned with the structure of the ecosystem beneath it. That alignment was its greatest strength and, ultimately, its greatest vulnerability. When the Chicxulub impact disrupted global climate and primary productivity, the change was not limited to temperature levels or light levels. It altered the flow of energy through ecosystems. Plants struggled to grow. Herbivore populations declined. Food webs collapsed from the bottom up. For organisms whose survival depended on flexibility, small size, or alternative food sources, these changes were survivable. For a large, specialized apex predator, they were not. This distinction lies at the heart of modern extinction science. Extinction does not occur because organisms are poorly adapted. It occurs when adaptation becomes too specific for a world that no longer exists. The case of Tyrannosaurus rex illustrates this principle with unusual clarity. At no point does the fossil record suggest that Tyrannosaurus rex was failing before the end Cretaceous event. There is no evidence of long-term decline, competitive displacement, or loss of ecological relevance. Instead, its disappearance aligns precisely with a global environmental shock that removed the conditions required for its survival. This alignment supports the prevailing scientific consensus. The Chicxulub impact was the primary trigger of the end Cretaceous mass extinction. Volcanic activity, particularly the Deccan traps, likely contributed additional environmental stress. Together, these forces reshaped Earth's surface environment in ways that favored small, flexible organisms and eliminated large specialists. Tyrannosaurus rex was among the latter. This conclusion does not diminish its significance. On the contrary, it elevates it.
Tyrannosaurus rex stands as a clear example of how evolutionary success is contextual rather than absolute. Adaptation solves problems posed by the present. It does not anticipate catastrophes. Natural selection does not equip organisms for every possible future. It equips them to reproduce effectively under prevailing conditions. When those conditions vanish, even the most refined adaptations lose relevance. This insight extends beyond paleontology. Mass extinctions have repeatedly reshaped life on Earth by removing dominant forms and opening ecological space for others. The rise of mammals following the end Cretaceous extinction is one such outcome. Small, adaptable mammals survived the crisis and diversified into niches once occupied by dinosaurs. Birds, themselves descendants of theropod dinosaurs, carried forward a transformed legacy. The extinction of Tyrannosaurus rex therefore marks both an ending and a beginning.
It closed the chapter on non-avian dinosaurs as dominant terrestrial vertebrates. It opened the path toward ecosystems structured around different principles of survival. Understanding this transition requires rejecting simplistic narratives of strength and weakness. Evolution does not reward power in isolation. It rewards compatibility with environment. The lesson of Tyrannosaurus rex is not that dominance is fleeting. It is that dominance depends on stability. When stability collapses, survival belongs to those whose requirements are minimal and whose strategies are flexible. This lesson remains relevant today. Modern ecosystems are undergoing rapid change driven by climate shifts, habitat loss, and altered energy flows. As in the past, large, specialized organisms face the greatest risk. The fossil record does not predict outcomes, but it offers perspective. It reminds us that extinction is not a moral judgment, it is a biological consequence. Tyrannosaurus rex did not fail, it simply reached the limits of what any organism of its kind could endure. In recognizing those limits, we gain a clearer understanding of how life persists and how it is lost. The story of Tyrannosaurus rex, then, is not a cautionary tale about power. It is a lesson about dependence. Life is sustained not by dominance alone, but by the conditions that make dominance possible. When those conditions change, survival follows a different logic. And in that logic, even the most formidable predator can vanish, leaving behind only bones and a question that science continues to explore.